G'day. Today I'm going to talk a little bit about cutting speeds. I'm a member of an online metalworking group. I'll put a link down below. And every so often we have someone come along who says, "Oh, I can't get this thing to cut," or why is this not working? And when we ask a few questions, it's typically about cutting speed. Cutting speed is one of those things that until you know about it, you don't pay any mind to it, and it's actually quite important. So I'll be showing you the formula behind cutting speed and a few of the things to think about when you are selecting what speed you're going to use. I guess firstly, what is cutting speed and how did it come about? It was, I guess, back done earlier last century. Once you started getting people chasing efficiency, you wanted to know what the optimum speed to run your tool at was in a balance between tool life and metal removal rates. And so the cutting speeds that you read of in books and see in charts are based on production environments, running high-speed steel tools usually against a cylindrical piece of metal in a lathe. That's the easiest way to do it. And it works out, okay, how big a chip are you taking off before the tool blunts, before the surface finish degrades or something like that. And that's basically where cutting speeds come from. So for something like mild steel, you're talking 30 metres a minute. If you're talking aluminium, we're probably talking about 90, 100 metres a minute. If you're talking something like cast iron, you might be down around about the 10, 20 metres a minute. It's not hard and fast, it's all been done empirically, and so it's really, you find a source that you trust and you use the numbers that they give you. This is a typical chart. It looks like it's come out of the Machinery's Handbook or something like that. It's actually off a website, American Machine Tools. I'll put a link to that down there. But what it's giving you is it's giving you materials, your cutting speeds, a bit of geometry for lathe and drill tips, that sort of thing, and also coolants that are used in an industrial environment. Now, in a home workshop, most of the cutting is, well, not most, is done dry. A lot of the time, in a lot of workshops, the cutting is done dry, so it's not necessarily, you can't necessarily get these speeds, but they're a good starting point. This is the metric version of the formula. So RPM is equal to 300 times by your cutting speed divided by your diameter. Now, rather than do this and having to remember a whole bunch of cutting speeds for different materials, what I typically do is put in a value of 30, which is the cutting speed for mild steel. So my equation just becomes 9,000 divided by the diameter of the cutter. And then what I do is I've memorised a few numbers, so I know that for aluminium it's 3 times the mild steel speed. I know for cast iron it's around about half, alloy steel's around about half, and so on. And so I just remember that formula, and then I just multiply the RPM up and down. On a lathe, the critical diameter is going to be the diameter of the work you're turning to, although if you have to reduce down to a diameter from a stock diameter, you need to start on the stock diameter. Now, if it's small enough or it's a separate operation like threading, you can then change your speed, but typically you'll start at your biggest diameter and set your speed based on that. For a drill, the diameter is going to be the diameter of the drill. That's going to be the maximum diameter that's going to, or the maximum point that's going to be cutting metal, and so therefore that's the diameter you use. If you're doing something like a hole saw, you'd use the diameter of the hole saw or that sort of stuff, bearing in mind that for hole saws they usually have a recommended speed anyway. For a milling cutter, it's the diameter of the cutter. Now, that's pretty straightforward for a straight cutter like this, which is an end mill. But if you have shaped cutters with angles on them, radii, all that sort of thing, it's the biggest diameter. It's basically what's the maximum tip velocity going to be. That was at 780 RPM, which is around about the correct speed for mild steel. And as you can see, the chips have come off in a sort of a spirally sort of thing. Moderate pressure not a big deal. This hole is at 260 RPM, so around about a third of the recommended speed. As you can see, the chips are still coming off quite alright. Probably a little bit more pressure. The way drill bit's cut is that the chisel point is what starts the hole, and so that's scraping as it goes in. So the slower it is, the more it has to scrape to get a decent cut. This trial was done at a bit over 3000 RPM, and the chips have come off a dark blue. Now the previous chips have come off shiny. Dark blue means it's overheating. If I continued that, I'd blunt my drill bit. Yes, it delivers a hole, but even then I can feel the drill bit is heating up. You can tell with this drill bit that it's copped a bit of abuse. It doesn't feel sharp at all to the finger there, as opposed to this one, freshly sharpened at the same time as this one. There's an edge there, you can feel it. So it doesn't take much to blunt a drill bit, and of course as it gets blunter it won't cut as well, it'll generate more heat, which makes matters worse. Now the numbers I've given so far are for mild steel. Carbide you can go lots faster, and fortunately on a packet of inserts you should have a speed here. So this particular one says 130 meters per minute for these particular inserts. That's fine. Usually for carbide I'll say, well, I'll just multiply by 3 or 6 or 7 or whatever the number is. Now remember, these two are speeds that theoretically you can go at, and particularly with carbide it'd be flood coolant, it'd be a very rigid machine and all that sort of thing. So for manual lathe use on a possibly even on a small lathe, you need to back these things off. Although one thing I have found with carbide, if your lathe is too small and you haven't got terribly much power, then sometimes it's pointless using inserts because you just can't push them through the work. Part of this assumes homogeneous materials that are uniform in their properties all the way through. This is a lump of cast iron I've got, and as you can see there's a great big void in there. Now that typically is going to be very hard, and so if I was running a drill bit through here and I didn't know that void existed, I'd likely blunt that drill bit very quickly, just because that's far harder material. So always bear in mind when you're thinking about your cutting speeds, what you're actually cutting, and is it really homogeneous or is it possibly not. And so for a casting where you've got a skin, that's going to be very hard, and so first of all you want to try and cut under the skin, but you also might want to slow your cutting speeds down a little bit, just to give your tool a little bit better chance of survival. So materials that will particularly give you problems, there are things like stainless steel, which can work harden. Now work hardening is basically the heat of the rubbing of the tool is enough to make it harder, and so you'll find that unless you've got sharp tools and you've got a decent rate of feed, you'll generally blunt your tools. Everything will get hot, this may go blue, may distort, your tools will certainly become blunt. So you need to think about this. A little bit of coolant sometimes helps, making sure your tools are sharp, making sure it's well supported so that the material can't push away from the tool. You need to have it well supported, and that'll usually get you past stainless. Then there can be materials that grab up the tool. And this is particularly if you're using drill bits and things where there's positive rake on the tool. So things like plastics can do it, as can brass. Okay, and typically when people talk about drilling brass, they say, "I'll get a stone and take the front edge off your drill bit." so it doesn't tend to grab. The only solution I have for those really is to basically make sure everything is clamped down properly, so that when you do drill and you maintain a decent rate of feed, it's not going to grab and pull its way up the drill bit. The other problem with plastics too is that it's a low melting point material, and so if your drill bit is slightly blunt, what you may find is that the material starts to distort. In that case, you might want to use some coolant, and coolant can be something as simple as some water. Once again, sharp tools help. It's just one of those things, you'll just have to try it. If you've got several holes next to each other, you might even think about, drilling one hole, putting some form of stopper in the form of a dowel pin or something in there, and drilling the hole next to it, just so you don't have the one hole sort of melt into the other. Another one, I haven't really got a decent example of this, but you might just see on the end of this drill bit how there's some metal there. And I think I've been using this to drill aluminium, and this is one of the problems you get with aluminium sometimes, is you get a built-up edge. And I've certainly come to grief parting things off where the aluminium is built up on the parting tool, particularly down the bottom of a slot, and then the tool doesn't cut, causes all sorts of problems. So the solution to that one is, once again, a bit of coolant for aluminium, some WD-40 or some kerosene or something like that, to try and prevent that edge building up, because it's the raw aluminium without any oxide trying to grab hold of the steel. With some of these things too, if you're drilling more than a couple of diameters deep, you want to do what's called peck drilling, and that's basically where you come down and you just dip the drill, for want of a better term, and let the chip break. Once you get over sort of 4 or 5 diameters of the drill, you probably want to pull it out every so often entirely to clear it, because you will get swarf building up in the flutes, which will stop the evacuation of the flutes. Another problem you can have is mystery metal. This bit's a bit of mild steel, this bit here is a bit of alloy steel, and as you can see, they don't look very different. And so whenever you're approaching a bit of mystery metal, you need to start off slow and move your way up in speed. You may find if you're trying to cut alloy steel at mild steel speeds, you're going to blunt your tools rather quickly. You need to be about half the speed that you would for mild steel. Mild steel, by the way, is just a catch-all name that applies to low carbon steels of a sometimes of a mysterious nature. It's mild steel. Some people say it's merchant steel, but it's typically garden variety steel that you can weld, you can machine, but the trade-off is your surface finish isn't necessarily as good. So what are the indicators that your cutting speed might be too fast? Well, usually if the cutting speed is too fast, the cutter goes blunt quickly, and so what you're looking for is things that would indicate a blunt cutter. So it could be things like your surface finish, particularly if it goes from a good surface finish to a bad surface finish in a small distance, that could suggest your cutter is blunt. And so you then look at perhaps your surface speed to see what that's doing. Your depth of cut might be reduced depending on how much of the cutter is being rubbed off. But once again, that could well be because your surface speed is too high. You might get some noise. Normal cutting, turning, you do get some noise, but it's usually of a continuous nature. So if you're parting something off, for example, you'll hear a sizzling noise. So if you're getting bangs or squeals or something like that, that would suggest that maybe there's some extra rubbing there, which would indicate a blunt cutter, which once again could mean that you're running your cutter too fast. You may get some sparks. I've had those with carbide cutters with chips out of them, inserts, and certainly if the cutter is blunt, you'll get extra heat building up in the workpiece. So that could also be an indicator that you're running the cutter too fast. And last of all is chatter. Chatter is when the workpiece is bouncing off the tool, or the tool's bouncing off the workpiece, and so the fix for that is generally reduce your speed, so the tool has a chance to cut rather than bounce. Thanks for watching. I hope this helps people understand cutting speeds and why they're important,
and please share and spread the word.